Hello, everybody. Great pleasure being here. And let me first thank the organizers for such a wonderful event. Actually, the title of my presentation in the booklet was just quantum computation of sparse matrix determinants, but now the title is changed. Now I will explain why, because they are connected to each other. Actually, two things makes my talk a little bit difficult now, because my talk is after the Nathan Webb's talk. He is a very good speaker, and the next thing is that my talk is before lunch, so perhaps people are looking forward to seeing the last slide of my PowerPoint. So I will try to make it faster, my presentation. So, okay. My work is actually, I'm a newcomer to quantum machine learning because my background is mainly neuroscience and open quantum systems. As I'm from Isfahan University of Technology, Department of Physics. Recently, I started working in this context to see if some quantum algorithms can be helpful for the pattern recognition, for example, some face recognition tasks. I'm happy. Oh. How can I change these? Maybe I should change it from here. Actually, this work is in collaboration with Professor Solano and also Michael Sanz. That the work is still in progress. And also two students, one is at Eskoltech in Russia and one at Isfahan University of Technology. So, can it be? USB is the only one, I think. Okay, no problem. I can change it in the keyboard. Okay, everybody here is familiar with pattern recognition, which has many applications in science, technology, and industry. For example, like fingerprint recognition, voice recognition by phone and, or computer, or some medical imaging, for example, some MRI imaging to recognition of some abnormalities in the brain, like tumors or some other diseases. And also some, for example, brain-computer interfaces to some feature extraction on brain electrical signals to make some task by a machine to be recognized. So it has many applications around, but I want to just focus on one of them, which is face recognition. Perhaps you have heard news that last month in China, there was the police in China using some special glasses that, which is equipped with facial recognition task, and they could arrest more than 30 wanted people during a month throughout the country. It was in news, so please be careful about Chinese participants. Perhaps they have something, the same thing here. And also, the Google Glass with facial recognition, perhaps in future when you go to a country you don't know anybody, so just with looking with people, you have the information about those people with names and also what they shared in the Facebook yesterday, something like this. Okay, last year, actually, there was a record by machine vision that the machines can see at least two times better than humans. And okay, actually these abilities of this machine vision is increasing just every year, and in future, perhaps we have more interesting applications by that. Okay, what is the difference between the human vision and machine vision? Actually, when we look at the face of a person, for example, Robert De Niro, just these lights from the face comes into our eyes by photoreceptors. These photons are absorbed, and then they are converted by electrical signals, and then through the neurons, they are received in visual cortex, and then after processing, consciousness happens, and we perceive that, okay, this is Robert De Niro, and this is what we perceive. But in machine vision, actually, the lights come into a camera, so they are received by some photodetectors, and then they are actually transferred to a PC, and there's an algorithm in the PC, so it receives the Robert De Niro just as a matrix. So what does a Robert De Niro is in a machine vision is just a matrix, so it's not a celebrity anymore. Actually, in machine learning, actually working is on data. Data are in the form of matrices and vectors. So the task actually is a mathematic based on that. So simply, if I speak about the face recognition, after taking a picture or after so making a video, so at some scene or in a picture, just the first one is the face detection. When the face is detected, then it will be normalized, and then some features are extracted. Now it's a sparse matrix, and then it goes to a database. So at the moment, for example, Google has a database composed of billions of pictures, and so they are labeled, and then a new other picture is taken. So again, the face detection, and then face normalization, and then feature extraction, but then it will be compared. So I want to talk about this matching, and then it decides, okay, these pictures belongs to which person. And this one is a database of billions of photos. Okay, so the face recognition steps, actually, we have lots of steps for face recognition, but simply you have database of faces, face detection, training, features matching, and so on. But two of this process, I think, are the most important issues. One is principal component analysis, or PCA, which is related to eigenfaces, and another one is independent component analysis that I will talk about it later. Okay, regarding the PCA, what is PCA? Actually, in a database, which is composed of the different faces, there will be a very big matrix, the millions, and that. So actually, it gives some eigenstates. So principal components, these principal components actually are some eigenfaces in a face space. So it gives this type, these are actually the eigenfaces, and the PCA gives us these principal components like average face, brightness, shadows, face direction, so in which direction, for example, is male, female, the gender. So it's based on the general features of a face, and each face actually can be expanded based on these eigenfaces, and just these weights are different for that. But in independent component analysis, or in ICA, actually it is relevant to some details in the face, like just they are independent to each other, not the whole face actually. It is like nose, eye, eyebrow, mouth, ear. So these signals actually are, these information can be discriminated. So ICA is related to partial properties and PCA to general properties. Another example regarding the ACA can be when you are in a party. So there are many different types of sounds coming to your ear, or to, and so for example, people are talking to each other, or there's somebody is playing music, or some noise of traffic coming inside. So how we can discriminate these voices, because they are coming as in a mixing state, so different sources, and we observe them. Now we want to actually determine which sound or voice is related to this source or this person. Okay, this is actually linear systems of equation. This is x equals to as, and for estimation of the sources, which is y, is equals to wx, this w is a inverse of that. So in the form of matrices, it can be like this. So in 2009, so the HHL algorithm was proposed. It has been cited, I think, close to 500. That is for linear systems of equation by the group of Professor Lloyd, these linear systems of equation can be solved with an exponential speedup. So these states, so perhaps quantum computation can be a help for these states. Now, the question is at the matching of faces, because these faces should be compared with each other, are they match or not. One of the mathematical tools is actually log determinant divergence, which is called dissimilarity, and also distance. When this distance actually closing to 0, so these two faces are actually better matched. And if this distance is large, so it means that these are not so similar. And if you look at that, for example, comparing two matrices or two vectors, x and y, so we have the trace of that log determinant and the dimension of these matrices. This is what we have. If d equals to 0, so two matrices are completely match. For example, we have a database of 4 pictures. This composed of George, Jeff, John, Tom, and so this, what is the name? Jeff. Okay, the Jeff, if you look at the distance number, so the other numbers is 158, the other one is 47, 253, and 252. So this 47 is the least distance among the others, so it is recognized that it is John, and the same thing for Tom. So this is what we need, is just to compute these distances. Also, we have different types of distance measures with different names. So for log determinant divergences, like geodesic distance, S divergence, power divergence, generalized Berg divergence, and generalized Lobsang, and different techniques. If you look at that, you can see that we need to compute in some relations the trace of these matrices and also the determinant of them, and to compute them, the log determinant of them, to compute these distances to see if these pictures are matched or not. Okay, so a problem can be reduced to computation of trace and determinant of matrices. Inspiring by the linear systems of equations by HHL algorithm, actually, first we want to say that if we can compute the trace of a matrix, actually the initial state can be prepared like that, doesn't actually, this first block is the quantum phase estimation, and the second one is inverse phase estimation, and in the middle is actually the rotation. So after that, so this process, after the Hadamard gates, after the control U, so we have these states. So based on, and after inverse quantum Fourier transform, so we have this term, so in which there's one of these k, actually if it is a perfect phase estimation, we have just as an x, which is matched with lambda tilde, that the lambda tilde actually has relation with the main eigenvalue of the matrices. So they are in superposition. So at the same time, all superpositions goes through this circuit. And after just rotations, this is in quantum evolution, they can be read as like that. So these eigenvalues can be, we don't need the inversion of the matrix like what is in HHL algorithm. So directly just writing these eigenvalues. And then after the inverse of phase estimation, and finally, as just the coefficient of cat1 can be the trace of A, and the projection of 1 can give us the trace of A. So with knowing the trace of A, actually based on this relation, we can also estimate the determinant of exponential matrix, a sparse matrix, with the complexity of log n. Another one can be to see if we can compute also the sparse matrix determinants. So actually the same things, but we should just actually somehow to have this multiplication of these eigenvalues. So again, with these initial states before the quantum phase estimation, so it goes through the Hadamard, and then the control U, again, the same things, and after the inverse quantum Fourier transform, then after the rotations, again, so we have this. So at this stage, we need to actually to run the algorithm n times, just one by one. Actually, it is in parallel lines, that in parallel lines actually like a tensor product. And just one of after this multiplication in this quantum evolution, it can be just the coefficient of 1 tensor n be the determinant. But actually, I didn't consider as in this formula the normalization factor. so I didn't write it here. And also in the case of if the phase estimation is not complete, if that eigenvalue is not actually equals to k over 2n. So the determinant by projection on one tensor can be measured. So with the complexity after that, actually, it can be in an n log n. So actually, we are still working on that to estimate some errors for these. Okay, so your comments are welcome because also Professor Lloyd is here and Nathan Weeb and other people who are expert here. So your comments are very welcome. As a summary, I think that it's, regarding the PCA, and again, Professor Lloyd proposed the algorithm for PCA and also ICA based on linear systems of equations. And for matching, we need to compute the trace and determinants of the sparse matrices. So I think the quantum computation can be a help, a good help, actually, for face recognition tasks. Okay, at the moment we have no quantum computer, but actually the next decade, who knows? Perhaps we have quantum computers with large numbers of qubits, so we can go into the real and serious quantum machine learning task. Also, if we know the determinant of a matrix, that it can be used for the calculation of area and volume of geometrical objects, also 3D data analysis for like MRI images, or Jacobi formula, or convex optimization, control engineering, and mathematical applications. Okay, thank you very much for your attention.